Welcome students. Today we'll be talking about the semi-empirical mass formula and the binding energy expression. So what is the semi-empirical mass formula? So this is a formula which gives us an expression for the mass of an atom and hence also for the atomic nucleus. So what we basically do is we find out the mass of an atom, subtract the mass of the electrons from it, and hence we get the mass of the nucleus, as because experimentally determining the mass of a nucleus is very difficult. So it's also called the Bethe-Weizsäcker formula, and it gives us an expression for the mass in terms of the binding energy of the nucleus, which is expressed as a series of terms. So when we discuss about the binding energy, if you remember, we found out an expression for the binding energy in terms of the mass defect. So there we had the mass of the nucleus in the binding energy expression and also the mass of the atom in terms of the mass of a hydrogen atom. If we can write the binding energy expression in terms of the atomic mass also. So this expression, it gives us the mass of an atom or a nucleus in terms of the binding energy, and the binding energy itself is expressed as a series of terms. So these different terms in the binding energy expression, it reflects different properties of the nucleus and are expressed in terms of the number of protons and number of neutrons in the nucleus. So basically what it means, the semi-empirical mass formula is a formula for the mass of an atom or hence for the mass of a nucleus in terms of the binding energy, and the binding energy is expressed as a sum of or as a series of terms, and each of these terms, they reflect some property of the nucleus, and nuclear properties, they're dependent on the mass number and the atomic number. So in this expression for the binding energy, what is done is the different terms representing different properties of the nucleus are expressed in terms of the atomic number and hence the mass number of the nucleus. So this formula is partly based on theory and partly on experimental measurements, hence the name semi-empirical. Empirical means experimental. So also this formula is based on the liquid drop model of a nucleus. So later we'll be discussing more about this liquid drop model. So this is a theoretical model of the nucleus in which the nucleus is considered to be analogous to a liquid drop. It has uniform density, it is incompressible, it's spherical in shape, but many other analogies are there between a liquid drop and the nucleus. So this is a theoretical model in which the nucleus is considered to be like a liquid drop. So the semi-empirical mass formula is based on the liquid drop model of a nucleus basically. Now going back to the binding energy expression for a nucleus, we had already discussed about this. The binding energy, which is dependent on the mass number and the atomic number of the nucleus, is defined by this expression. So binding energy is Zmp, mass of the proton, and Mn, n is the number of neutrons, Mn is the mass of the neutrons, minus m dash Az, this is the mass of the nucleus. So analogously, this expression for the binding energy can also be written in terms of the atomic mass. So if we write it in terms of the atomic mass, here atomic mass is nothing but the nuclear mass plus Z times the mass of electrons. If there are Z protons in the nucleus, there will be Z electrons. So this is the total atomic mass. So this mass of the nucleus here can be expressed in terms of the atomic mass. So the binding energy expression in terms of the atomic mass can be written as BAZ is equal to this, where mH now, not mp, mH is the mass of a hydrogen atom. So what it basically means is we are adding and subtracting ZMe in this expression. So Mp plus of Me gives me the mass of a hydrogen atom. So ZmH here. So this expression gives us the binding energy in terms of the atomic mass. Now, the semi-empirical mass formula, as we have talked about, is a formula for the mass of an atom. So once we find out the mass of an atom, we can easily find out the mass of a nucleus. So from the earlier expression here, we are bringing the binding energy term this side. So MaZ in mass of an atom is equal to ZmH plus Nmn minus Baz by C square. So Baz is the binding energy of the nucleus. So in the semi-empirical mass formula, the binding energy of the nucleus is expressed as a sum of 5 terms. Already we have talked about it. Each term, it represents different properties of the nucleus. And these terms, which constitute the binding energy, are expressed in terms of the atomic number, mass number, and hence the number of neutrons. So these terms, they have specific names to them. The binding energy, as I told you, is a series of terms, is the summation of all these terms. First term is the volume energy, 5 terms. Second is the surface energy. Third is the Coulomb energy. Fourth is the asymmetry energy. And fifth is the pairing energy term. So each of these terms, they represent some property of the nucleus, and it contributes to the total binding energy of the nucleus. So the formula for binding energy is given by, this is the actual formula in terms of mass number and the atomic number. So Baz, AVV, AV is the volume energy constant. So this is the expression for the volume energy. This is AS is the surface energy constant. This is the surface energy term. This is the Coulomb energy term. AC is the Coulomb energy constant. ASYM or AS is the asymmetry energy constant, and this is the asymmetry energy term, and this is the pairing energy term. Here we can see that AVV, the volume energy term, is a positive term. The other terms are all negative contributions to the binding energy. They try to destabilize the nucleus. So now we will look into all these terms one by one. So what is the volume energy term? So the volume energy term, it arises because of the strong nuclear interaction between the nucleons in the nucleus. So what it basically means is that inside the nucleus, the nucleons, that is the protons and the neutrons, they are held together by strong nuclear forces. So each nucleon is interacting with some other nucleons in the nucleus. So this volume energy term, this is a positive attractive interaction. Because of the nuclear force, each nucleon attracts another nucleon. It is independent of charge. So this is an attractive interaction which binds together the nucleus. Now each bond has a particular bond energy, so that contributes to the total binding energy of the nucleus. So this volume energy is proportional to the number of nucleons in the nucleus, and hence volume. So this term is called the volume energy term. Why it is so? It is because more the number of nucleons in the nucleus, more will be the internucleon bonds. So more should be the binding energy or the total bond energy of the nucleus. So this energy term, which is proportional to the volume of the nucleus and which arises because of the attractive interaction between the nucleons due to the strong nuclear force, is called the volume energy term. Now, as we talked about the semi-empirical mass formula, it is based on the liquid drop model of a nucleus. And in this liquid drop model, the nucleons are considered to be spheres of equal radius, and these spheres, the nucleons, are closely packed inside the nucleus. Now, if we know about the closed packed structure from solid state physics or otherwise also, if we pack spheres, suppose in a container, we can consider marbles, equal sized marbles closely packed in a container, then each marble will touch 12 other marbles. So in other words, equally sized spheres in a closely packed structure, each sphere it is in touch with 12 other spheres. Now, in the case of the nucleons, therefore, as they are closely packed inside the nucleus, each nucleon it touches 12 other nucleons, or in other words, they interact with 12 other nucleons. Why so? It is because the nucleons, they interact via the strong nuclear force, and this nuclear force, a particular characteristic of the nuclear force is that it is a short range force. So, one nucleon can interact only with 12 other nucleons. Now, if the bonding energy between two nucleons because of the internucleon strong nuclear force is U, then per nucleon the bonding energy will be half U. Again I am telling you, if I have two nucleons, they are interacting via the strong nuclear force, the strength of the bond is U between two nucleons. So per nucleon the internuclear bond strength will be half of U. Now, each nucleon is interacting with 12 other nucleons. So from each bond for the nucleon, it is getting the bond strength of the bond, the bonding energy is half U. So if we consider all the 12 nucleons with which a single nucleon is interacting with, the total bond energy per nucleon is 6U, that is half U into 12, that gives you 6U. Now, if A is the mass number of the nucleus, that is, if A is the total number of nucleons present in the nucleus, then the total binding energy, that is because of the strong internuclear bond in the nucleus, is equal to 6A into U. So basically what this means is 6U is the bonding energy per nucleon. There are A nucleons in the nucleus, so total bonding energy because of the strong nuclear force for the whole nucleus with A nucleons is 6AU. This strong attractive bonding energy is called the volume energy term for the nucleus. It is a contribution to the binding energy of the nucleus, so it binds together the nucleus. So the volume energy is equal to 6AU, or we can write it is equal to AVA, where AV is called the volume energy constant. After talking about the volume energy term of the nucleus, that is a term in the binding energy expression, let's talk about the next term, that is the surface energy term of the nucleus. So this surface energy term is a term in the binding energy which arises because of the finite volume of the nucleus. That is, this is a correction term to the binding energy expression. So when we talked about the volume energy term of the nucleus, we considered that each nucleon inside the nucleus is interacting with 12 other nucleons. This will be true, means all the A nucleons in the nucleus are interacting with 12 other nucleons. This will be true if and only if the volume of the nucleus is infinite. However, this is not true because every nucleus has a finite volume and hence it has a surface. The nucleus has a surface, finite surface area. So what it basically means is that the number of nucleons or the nucleons residing at the surface or near the surface of the nucleus, it is not interacting with 12 other nucleons. Only the nucleons at the interior of the nucleus will interact with 12 others. So when we found out the volume energy expression, we did not take this into consideration. So the volume energy or the binding energy that we found out by considering that all the nucleons are interacting with 12 other nucleons needs to be corrected by a term, and this term is called the surface energy term. This is a correction term to the binding energy expression. So this surface energy term is proportional to the surface area of the nucleus and hence the name. Why? Because larger the surface area of the nucleus, more will be the number of nucleons residing near the surface and hence more will be the correction to the binding energy. So this comes from the name surface energy term comes from this, because the surface energy term is proportional to the surface area of the nucleus. It is a correction term to the binding energy of a nucleus. So as I have already told about, it arises because the nucleons at the surface has fewer neighbors than those at the interior of the nucleus. Now, if R is the radius of the nucleus, then the surface area of the nucleus, considering it to be spherical in shape, it is A is equal to 4 pi R square, where R is equal to R naught A to the power 1 by 3, where A is the mass number of the nucleus. So this expression is the expression for the radius of a nucleus with mass number A, and this is the radius constant. This is around 1.5 femtometer, 1.5 into 10 to the power minus 15 meter. So the surface area is 4 pi R naught square A to the power 2 by 3. So the surface energy term can be written as ES is proportional to 4 pi R naught square A to the power 2 by 3, or we can write ES, that is the surface energy, to be equal to minus AS A to the power 2 by 3. AS is the surface energy constant, and the negative sign here comes because this is a correction to the binding energy expression. So let's go ahead to the next term in the binding energy expression. This term is the Coulomb energy. So the Coulomb energy arises because of the electrostatic repulsion between the protons in a nucleus. So inside the nucleus, we are talking about the nucleons being present. So these nucleons can be either protons or the neutrons. The protons are positively charged, neutrons are neutral. So these protons, although they are under the influence of the strong nuclear force, the strong nuclear force predominates inside the nucleus, we can't discount the fact that these protons are positively charged, and hence the electrostatic force of repulsion between the protons held together within the short dimensions of the nucleus. The electrostatic force of repulsion will be there, and this electrostatic force of repulsion will try to destabilize the nucleus. So the binding energy expression needs to take this into account. So this again is a correction term to the binding energy expression. So the Coulomb energy is nothing but the electrostatic energy of a charged sphere of charge Ze. Nucleus of atomic number Z will have a positive charge Ze. So when we assemble a charged sphere of radius charge Ze, it will have its electrostatic energy, the amount of work that is done in assembling this sphere. So this energy itself is equal to the Coulomb energy of the nucleus, and it is a correction term to the binding energy. More the Coulomb energy of the nucleus, less stable will be the nucleus. So this term is called the Coulomb energy of the nucleus. Now, if the radius of the nucleus is r, then the charge density of the nucleus can be written as charge by volume. Considering the nucleus to be a sphere, the charge density can be written as this, Ze by 4 pi by 3 r cube. So the electrostatic potential at the surface of a sphere of radius r less than r is given by this. So what we are considering here is that we have to find out this is a standard problem in electrostatics, to find out the Coulomb energy or the electrostatic energy of a charged sphere. So we are building up this charged sphere. So what we are considering is that at any point of time, so what we are considering is at any point of time, let us say that we have a sphere of radius r. We have formed a sphere of radius small r. So total, we want to form the nucleus of total radius capital R. Finally, we want to form the nucleus of total radius capital R. So initially we are saying that we are forming the sphere. So initially let us say that we have a small sphere of radius small r. So the electrostatic potential, if Q is the charge, the electrostatic potential of this small sphere will be Q by 4 pi epsilon naught r. Now Q is the charge within this sphere, so it's 4 by 3 r cube, that is the volume of the smaller sphere, into the charge density 4 pi epsilon naught r. So this expression gives us the potential on the surface of the smaller sphere. So if I want to make the nucleus of total radius r, we imagine that on top of this smaller sphere, we put a layer of thickness small dr. We put a layer of thickness dr on top of this sphere. So the charge on this layer will be 4 pi r square dr into rho. So what basically we do here is we have a smaller sphere. On top of that smaller sphere, we have this smaller sphere. On top of this smaller sphere, we put a layer of thickness dr. Okay, as because it's a spherical surface, the volume of this small layer of thickness dr will be 4 pi r square dr, and rho being the charge density, dq will be the charge on this layer. So what is the work done in putting this layer of charge dq on top of the smaller sphere of radius r? So the work done will be nothing but v into dq. So this is a standard problem in electrostatics, as I told you. So this is the work done in the process. So the total work done in assembling the whole sphere, that is the whole nucleus of total charge Ze, and hence total radius r, can be obtained by integrating this expression from 0 to Ze, that is integrating this expression, small r is the variable, from 0 to r. So once we do the integration, if you do this integration, r to the power 4 dr, you will end up with this expression. You can do that and verify. So the Coulomb energy of the nucleus can be written as Ec is equal to minus A3, E is a constant, pi 4 epsilon naught is a constant, R can be expressed as R naught a to the power 1 by 3, that is the radius expression. So the Coulomb energy can be written as A3 Z square by, small a3, that is the Coulomb energy constant, or in some books they write it as AC Z square a to the power 1 by 3, where R is the radius of the nucleus. So this expression gives us the Coulomb energy term. So here, this one we can call it AAC with a small subscript c. We'll call it the Coulomb energy constant. Probably later in the lecture I have consider it to be AC. So that is the Coulomb energy of the nucleus. The next term, the binding energy expression, is the asymmetry energy. So what is usually found is that in lighter nuclei, the number of protons and the number of neutrons are same. However, when we go for heavier nuclei, it is found that there is an asymmetry in the number of protons and the number of neutrons. The degree of asymmetry is represented by n minus z. So n minus z usually increases when we go for heavier nuclei. So this is because if more number of protons are there, the Coulomb energy will be more, so the nucleus will be unstable. However, asymmetry in the number of protons and neutrons also increases the energy of the nuclear system, by an amount which is called the asymmetry energy. So what it basically means is, from lighter nucleus to heavier nucleus, if I want to, heavier nucleus means the mass number is more, n plus of z is more. So three ways of doing it. One is increase the number of protons and neutrons equally, so that A is equal to n plus of z increases. Second is keep the number of protons very less and keep on increasing the number of neutrons. Third is keep the number of neutrons very less and keep the number of protons, increase the number of protons. The third possibility nature does not follow, because increasing the number of protons destabilizes the nucleus. So what nature usually follows is keep the number of protons less and increase the number of neutrons. But does it mean that I can keep proton number 1 and keep on increasing the number of neutrons? It is not so, because the asymmetry between the number of protons and the neutrons increases. And what has been found is that even this asymmetry, as I have told you here, the asymmetry in the number of protons and neutrons, also it increases the energy of the system, making it unstable. So it's a compromise between both. So the proton number also increases, but the neutron number increases more than the number of protons. So nature follows a balance between both, a balance between the Coulomb energy and the asymmetry energy. No doubt, the asymmetry in the number of protons and neutrons will destabilize the nucleus, but increasing the number of protons too much also will make the nucleus more unstable by increasing the Coulomb energy. So what is usually found is that number of protons also increases and the number of neutrons also increase a bit more than the number of protons. So this is the balance that occurs in nature. However, this asymmetry in the number of protons and neutrons increases the energy of the system, and the binding energy expression needs to take this into account, the instability that is introduced in the nucleus because of the asymmetry in the number of protons and neutrons. So an energy term called the asymmetry energy term is there in the binding energy expression, and this asymmetry energy term is proportional to the asymmetry between the number of protons and the neutrons, and it is called the asymmetry energy term. So find an expression for this asymmetry energy term. We have to go a bit beyond the liquid drum model of the nucleus. We have to consider what is called the shell model of the nucleus and Pauli's exclusion principle. We won't go into the details of the shell model as of now, but what it basically means is that the protons and the neutrons, or the nucleons inside the nucleus, they reside in energy shells. Just as the electrons in an atom, they reside in energy levels, energy shells, so also the protons and the neutrons, they reside in energy shells. And these proton and neutron shells are independent of one another, and the number of nucleons that can reside in each shell is limited by Pauli's exclusion principle, because the protons and the neutrons, they also are fermions. They have to obey Pauli's exclusion principle. So we need this basic idea of the shell model and the Pauli's exclusion principle to explain or to find an expression for the asymmetry energy. So this is the asymmetry that we are talking about. Simple example, let us say for a nucleus, A is equal to 16, that is the mass number. So these two possibilities are there, number of protons, independent shells, first level, they are filling up. Number of protons is 8, number of neutrons 8. So here, this is the symmetric nucleus, M minus Z is equal to 0. In this case, number of protons is 6, but the number of neutrons is 10. So there is an asymmetry of 4. However, from this nucleus, if we want to get this nucleus, these two protons need to be replaced by neutrons. But these neutrons can't be in the same level as that of the protons they are replacing, because this level is already filled. So these neutrons, the new neutrons replacing these two protons, they need to go to a higher energy level. So the sum total of the energy of this nucleus is more than that of the symmetric nucleus. That's a simple explanation for the asymmetry energy. Again, I am telling you, here number of protons and neutrons are same. Here mass number is same, but the number of neutrons are more. So to get this nucleus from the symmetric nucleus, we need to replace these two protons. So two protons, if I have to replace it by two neutrons so that A remains the same. So these two protons were occupying this energy level, but the new neutrons that I am replacing these two protons with, they have to go to the higher energy level. Why? Because this level, the level of the protons, this level is already filled. So the new neutrons, they occupy a higher energy level. So as a whole, if we see, the total energy of the nucleons in the nucleus is more than that in the symmetric nucleus. So that is the asymmetry energy. So we need to find out an expression for this. So let us consider this example. We have two nuclei, one where n is equal to z and the other in which n is not equal to z. So these are the n levels and these are the p levels. This is the symmetric nucleus, as we discussed, 246 neutrons, 246 protons, 12, mass number is 12. So if I want to produce a neutron excess of n minus z is equal to 8, right? If I want to produce a neutron excess or asymmetry of 8, I have to replace 4 protons by 4 neutrons. So without changing A, so half n minus z, that is 4 neutrons, would have to be replaced, would have to be replaced by protons in the original nucleus where n is equal to z. So these 4 protons need to be replaced by 4 neutrons. Okay? So here these 4 protons will have to be replaced by 4 neutrons. These 4 new neutrons will occupy higher energy levels. So the new neutrons will occupy energy levels higher in energy by 4 epsilon by 2, that is 2 epsilon. Let us say the distance between the energy levels is epsilon. So these 2 protons are replaced by neutrons which are occupying higher energy levels. How much high? 1 epsilon, 2 epsilon. Again, these 2 protons need to be replaced by neutrons which are occupying still higher energy levels. How much high? These 2 protons were in this level, 1 epsilon, 2 epsilon. So the new neutrons will occupy levels higher in energy by 4 epsilon by 2, that is 2 epsilon. So in general, each of the half n minus z new neutrons must be raised in energy by half n minus z epsilon by 2. In this case, n minus z is 8. So each of the 4 new neutrons must be raised in energy by half, if I put it 8 to epsilon. So this is a particular case where we are considering n minus z is equal to 8. So in general, if I have a nucleus, or if I want to create an asymmetry of n minus z, half n minus z new neutrons must be raised in energy by half n minus z epsilon by 2. So the total increase in energy for an asymmetry of n minus z in general is equal to, let's call it dE, that is the total increase in energy, is equal to the number of new neutrons into energy increase per new neutron. So if we put it back, the number of new neutrons for an asymmetry n minus z into the energy increase per neutron, that is equal to epsilon by 8 n minus z whole square. So this energy arising because of the asymmetry in the nucleus is called the asymmetry energy term. So n, we are writing it in terms of z, or sorry, a and z. So n is equal to a minus z. So this expression becomes this. Now, greater the number of nucleons, smaller is the energy level spacing. This from atomic physics also we know. Higher energy levels are closely spaced. So if the number of nucleons are more, if the mass number in the nucleus is more, they will occupy higher energy levels. So epsilon will be less. That is, epsilon is inversely proportional to A. So the asymmetry energy term can be written as minus of dE, that is equal to minus AA, is called the asymmetry energy constant, A minus twice z whole square, and epsilon is proportional to 1 by A, so the A comes here. So this is the asymmetry energy term. The last term of the binding energy expression that we will talk about is the pairing energy term. So this pairing energy term is to take into account the experimentally observed fact that even nucleus are more stable than odd nuclei. Even nucleus are more stable and odd nuclei are least stable. So nucleus can be even odd even, and odd. That means it can have even number of protons and even number of neutrons, and odd means odd number of protons and odd number of neutrons. Even odd means even number of protons and odd number of neutrons. Odd even means odd number of protons and even number of neutrons. So what is experimentally observed is that even nuclei, they are more stable, and odd nuclei are least stable. Odd even and even odd, they have intermediate stability. This hints to the pairing of like nucleons. So this is something which we have already talked about. Binding energy of even nucleus is greater than binding energy of even odd, or odd even is greater than the binding energy of odd nucleus. So like nucleons, they pair up. So nucleons, they pair up inside the nucleus. So to take this into account in the binding energy expression, the fact that even nucleus are more stable, odd nuclei are least stable, we need a term in the binding energy expression which is called the pairing energy term. So this pairing energy name comes because of the fact that pairing takes place among like nucleons inside the nucleus. So that's the explanation for this experimentally observed fact that nucleons, they pair up. Two protons will pair up, two neutrons will pair up. So even all the nucleons are paired, odd last one nuclei, proton and neutron, are left unpaired. So to take this into account in the binding energy expression, the pairing energy term is included. It's of the form del AP is the pairing energy constant, a to the power minus 3 by 4. Right? This is experimentally observed that this pairing energy term is proportional to 1 by a to the power 3 by 4, where a is the mass number of the nucleus. So for even nucleus, this is positive, it's stable. For even odd and odd even nucleus, the pairing energy term is 0. For odd nuclei, it's negative. That means that value of del for even it is positive, for even odd or odd even it is 0, and for O dot nuclei it is negative. So this is called the pairing energy term. So the final expression for the binding energy, taking all these terms into account, bringing them all together, is this. This is the volume energy term, surface energy term, Coulomb energy term, asymmetry energy term, and the pairing energy term. So if we plot all these terms, this is the volume energy, this is the surface energy, Coulomb energy, asymmetry energy. Bringing all of them together, we get the final binding energy curve that we talked about, the binding energy per nucleon variation with mass number. This is a very important figure, the contribution to the binding energy, final binding energy of a nucleus because of all these terms, corrections due to all these terms. We get the final binding energy expression. And the values of these constants, the volume energy constant, the surface energy constant, the Coulomb energy constant, this is the asymmetry energy constant, and the pairing energy constant. These are experimentally measured values. So this is all about the semi-empirical mass formula and hence its relation with the binding energy. So just to wind up, the semi-empirical mass formula is a formula which can give us the mass of the atom and hence the mass of a nucleus in terms of the binding energy, and the binding energy in this formula is expressed as a sum of 5 different terms, each of these terms representing certain specific properties of the nucleus. So this is all about the semi-empirical binding energy formula. So you may be asked individually about the different terms of this binding energy expression also. So thanks for your patient listening.